Hey friends, it's good to be back with you. And now let's take a little bit deeper dive into complex numbers, and let's figure out how to work with maybe more complicated functions using complex numbers. Now, one I kind of teased a little earlier is how in the world do you find the square root of a complex number? What is that? Well, it turns out once you see the process, it's not very hard. Now, it's tedious, it's not very hard. Okay, so the square root of a complex number, whatever it is, it's going to be the form a plus ib. Whatever it is, we can expect that the square root of a complex number itself will be complex. Now, if we're lucky, maybe one of the two of those will be equal to 0, but probably not. So what we're trying to do now is the game we're playing is we're trying to solve for a and b. Well, how are you going to do that? Now, let's see. What if I took the square of both sides? Okay. I think you might be able to see where this is headed. All right, okay, that's looking good. So that must be, let's see, a squared plus 2ab minus I squared b squared. I'm sorry, plus I squared b squared. There we go. I'm getting ahead of myself. Well, I squared is minus 1, so that's a squared minus b squared plus 2ab 1 plus I. A and B, we got two unknowns, don't we? And the whole point of algebra is if you got two unknowns, you got to have two equations, right? We do. It's just not obvious. If this side is to equal that side, it means the real part of this side has to equal the real part of that side, and the imaginary part of this side has to equal the imaginary part of that side. Oh, now I'm going to get two equations. So let's do the real part first. Well, 1 has to equal a squared minus b squared. And for the imaginary, let me try that again. There we go. Let's see. 1 has to equal 2ab. Okay. Now I got two equations and two unknowns. All we're trying to do now is solve for a and b. And you can do this a couple of ways. This gets pretty tedious, but let's at least get started here. B has to equal 1 over 2a from right there. So b squared has to equal 1 over 4a squared. All right. So what's this look like? Let's put that and substitute in right there. So 1 has to equal a squared minus b squared, which is that. All right, now we've got one equation and one unknown. Well, how are we going to solve this? I don't know any other way to do this but to multiply through by 4a squared. So I get 4a squared equals 4a to the 4th, oh, ick, minus 1. Now I have a fourth order equation. Okay, well, here, let's keep going. So 4a to the 4th minus 4a squared minus 1 equals 0. Well, I don't need, notice that a squared appears there and it appears squared there. Well, how about if we do this? Let's say c equals a squared. So this is now 4c squared minus 4c minus 1 equals 0. Okay, so you can back out a squared, and from there you can back out b. When you run through all this, I don't want to have don't need to watch me do all this by hand here. Let you get a good look at that so you can see where we're headed. If you solve all this, what you wind up with, I'm looking at my screen here to make sure I get it right, is equals, okay, 1.099 plus 0.455i. Now, if I did that right, that's the same answer I got before. And one more thing we have to realize here when we're dealing with square roots, if I type in to MATLAB or MathCAD or whatever my favorite number crunching program is, if I type in square root of 4, it's going to give me 2. By tradition, by custom, we generally only spit out the positive square root. But this is really the answer, plus or minus 2. Minus 2 times minus 2 is 4. And it's the same way here. Even though when you go into MATLAB, MathCAD, your calculator, whatever, you're going to get what's in the parentheses, that's really the answer. It's plus or minus that. Either one of those is the solution to that. So let's maybe pause here. I'm going to erase my board, and let's go to some other functions of complex numbers. Now, when you're working with complex numbers, by far the functions you see the most, apart from just multiplication and division, you'll see exponential, sines, and cosines. Those are around enough that it makes sense for us to learn how to deal with them. Now, they all become tractable in a very simple way. There's a relationship between exponents, sines, and cosines that's not at all obvious, but it's very, very important. In fact, as engineers, flight test engineers, whoever you are, you're going to use these probably all the time, but they're probably buried inside software. So it's there, but you're not necessarily seeing it. It's kind of transparent to you. But here's the thing. It's called the Euler relation. Okay, Leonhard Euler was one of the great mathematicians of the ages. This is how you write his last name. If you're German, you're going to pronounce that as Euler. In the United States, sometimes you hear it pronounced Euler. If you were to meet him and you had said, "Hey, Herr Euler," he's not going to know who you're talking about. So it's pronounced Euler. If you don't mind, I hope it's not pedantic. I'm going to say it that way. I took just enough German classes. I just don't have it in me to call it Euler. So anyway. He discovered this. Okay, now where this came from, we're actually going to do this later when we get into infinite series. But he took infinite series approximations of cosine and sine and just simply substituted ix into it. And what he got was this. Now, is this intuitive? Absolutely not. Does this have some kind of geometric, physical interpretation? Maybe. I'm not sure I could tell you what it was. This is one of these very, very fundamental relationships. It's absolutely true, but you're probably going to be frustrated if you start asking yourself questions like, yeah, I see it, but what does it really mean? What is it really describing? It doesn't mean anything more than this. This is a mathematical relation that happens to be true and is insanely useful. Looking for any sort of physical significance in it's probably not going to go anywhere. So let's say you want to calculate the exponential of some complex number. Let's make it really simple. Let's say e to the 2i perhaps. So if you're trying to calculate e to the 2i, what you're really doing is saying cosine of 2 plus I sine of 2. No problem. No problem at all. Okay? Calculator knows how to do that. Your calculator knows how to do that. Now, if you want to look into this a little deeper, what happens if I put pi in there? Well, e to the I pi is cosine pi plus I sine of pi. Well, what do I get? Well, let's see. E to the I pi equals minus 1. I think, because that goes to 0. Well, I'm going to make one small change to this. And for reasons that I'm probably not qualified to explain, many mathematicians believe that to be the most beautiful equation in mathematics. As an engineer, I look at it and go, what's it good for? Well, not much. But to a mathematician, the beauty lies in the fact that the 5 most important constants in mathematics, 0, 1, I, pi, and e, all appear in one equation with nothing else. So when you start looking at complex functions, this is probably where you're going to be most of the time. Now, before we move on, I had mentioned that there was another way to multiply and divide complex numbers. Now, before we had used the example of 1 plus I times 2 minus I. And that certainly works. We got 3 plus I. Now, just so you know, when you see me look down like that, I'm looking at my monitor to make sure I get this right. There's probably somebody out there who can work through all of this without making a mistake. I apparently am not that guy, so I'm kind of looking at my cheat sheet over there to make sure I get this right. Now, there's another way to do this. If you draw out a complex number in a real and imaginary axes like that, okay? Let's see, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, there. Real and imaginary. Well, 1 plus I is right there. All right, that's 1 plus I. Where's 2 minus I? 1, 2 minus I. So right there. That's 1 plus I, and that's 2 minus I. Okay, right on this coordinate system I've got drawn here. All right, I'm going to zoom in on 1 plus I for a second. Can we do that? I'm going to zoom way in here, draw this bigger. Okay, so that's real and that's imaginary right there. And there's 1 and there's 1. So there's 1 plus I. All right, all I did was zoom in. Get this out of your way. There's another way to write this, isn't there? Wouldn't that be a radius? You see where I'm going here. This sure looks like polar coordinates, doesn't it? Huh. So what's the radius? Well, it's the absolute value of the real number, of the imaginary number. What's the the absolute value is just the length of that vector there. And those are the components. So we're looking at Pythagorean theorem here, aren't we? So let's see, 1 plus squared plus 1 squared. Boy, that sure looks like the square root of 2 to me. Well, what's theta? Well, that's the inverse tangent of that divided by that. Okay, that's 1 over 1. That's okay, no problem there. That's 45 degrees, fair enough. But we're never going to write this as 45 degrees when we're working with functions like this, because that's not a natural unit of angle. We want to write this in radians. So it also turns out to be, and again, I'm going to look at my screen here, 7854. And I'll put radians there just so you know what that is. Okay, that should be pi over 4. Okay, so there's another way to do this. That's if we can write out a complex number in what we call rectangular or Cartesian coordinates or in polar coordinates, when we multiply them in Cartesian, couldn't we multiply them in polar? You bet. Here's how this works. Let me erase my board here. Okay, so if I have Z1 equals 1 plus I and Z2 equals 2 minus I, well, let's see, I could have a radius 1 and a theta 1, and here's how you write that. This should be a straight line, sorry. All right, that's how that works. I can write this out as R1 theta 1 and R2 theta 2. That's equivalent to A plus IB like we've seen before. So Z1 times Z2 equals R1, R2, and the angle, that's a terrible 2, theta 1 plus theta 2. That's all there is to it. All right, so R1 is the square root of 2, so that's 1.4141 or 2. 2. Okay, that's R1. R2 is 2.2361, and that's the square root of 5. So it's 2 squared plus minus 1 squared. So 4 plus 1, square root of that is 5. So that's the square root of 5. Well, theta 1, we already know. That's 0. What did I say that was? 7854. And theta 2, what's terrible theta? Now theta 2 is going to be a negative number. And the reason it's going to be a negative number is that the vertical component, the imaginary part, is negative. So it's going to be below the horizontal axis, as I drew that before. So for theta 2, we're going to get minus 0.4636 radians. All right, what's that going to be? Well, it looks to me like it's going to be 1.4142 times 2.236, and the angle is going to be 0.7854 minus, oh boy, this gets old, 4636. Okay, and that's true. That's the right answer. And what we're going to get here, let me check my screen. 1623, 0.3218. Okay, now, how do I turn that back into A plus IB? Because it's okay to write it like this, but we're eventually going to need to find out what the real and the imaginary parts are. So let's keep this, and let's chuck the rest for right now, because I need some more acreage here on my board. Get rid of all this. Now let's see. If I know that that's A, and that's B, and that's theta, and that's R, well, let's see. A must be R cosine theta, and B must be R sine theta. And when you work this all out, if you say Z equals R cosine theta plus I times R sine theta, what you get is 3 plus I, just like we got before. All right, well, that worked pretty well. How would you divide? It's almost the same thing. Okay, for division, we're following the same kind of pattern, and your intuition may help you here. You may be able to anticipate what I'm going to write. So if I say Z equals Z1 over Z2, and that's 1 plus I divided by 2 minus I, well, what I can do here is in polar, Z equals R1 divided by R2, theta 1 minus theta 2. That's it. And when you do that, you get the same answer that we got when we worked it out in rectangular coordinates. Okay, so the MATLAB implementation of this is going to be pretty straightforward, but for completeness, let's go ahead and do that.